Good morning, ladies and gentlemen. We will begin the opening ceremony for this event. So please come to the ballroom. Good morning, ladies and gentlemen. First of all, I would like to introduce myself. My name is Tessa, and I will be your master of ceremony for this event. So on behalf of the organizers, we would like to extend our warm welcome to all the guests of 8th International Symposium on Current Progress in Mathematics and Natural Sciences, ISCPMS 2022, hosted by the Faculty of Mathematics and Natural Sciences, Universitas Indonesia on August 24th until 25th, 2022. So in this occasion, I would like to welcome our honorable guests, the Dean of the Faculty of Mathematics and Natural Sciences, Universitas Indonesia, Pak Dede Johana, PhD, the Vice Deans of Faculty of Mathematics and Natural Sciences, our honorable speakers who are here with us today, Prof. Muhammad Khairuddin Arawa from Sunway University, Malaysia, and also Dr. Sabikah Anwar from University Malaysia, Terengganu, Malaysia. So to the other honorable speakers who are with us through the online Zoom meeting, Prof. Shandar Ahmad from Jawaharlal Nehru University, India, Dr. Jong Myung-ha from Korea Institute of Science and Technology, Korea, Dr. Fatwa Firdaus Abdi from Helmholtz Zentrum Berlin, Germany, Eric Vance, PhD from University of Colorado, USA, Prof. Dong Hyun Kim from Chungbuk National University, Korea, Prof. Peter Barlow from Edinburgh Napier University, UK, and Dr. Richard M. Paulin from University of Oxford, UK. We also welcome all the lecturers, guests, students, and all of the participants. Ladies and gentlemen, before we proceed further this morning, I would like to invite all the participants to please raise and then sing the Indonesian national anthem, Indonesia Raya. You can all please sit. So before we begin, it would be better if we pray first. So we have to pray according to each religion and belief. Pray, begin. Finish. Thank you, everyone. Ladies and gentlemen, to begin with, I would like to invite Dr. Dipo Aldila, the chair of the 8th ISCPMS 2022, to deliver his welcoming speech. We would kindly invite Dr. Dipo to please come forward.
Bismillahirrahmanirrahim. In the name of Allah, the most gracious, the most merciful. Assalamualaikum warahmatullahi wabarakatuh. Dear Vice Rector for Research and Innovation, Ibu Miftami, PhD, Dean of Faculty of Mathematics and Natural Science, Universitas Indonesia, Pak Dede Juhana, PhD, Vice Dean of Faculty of Mathematics and Natural Science, Universitas Indonesia for Academic, Research, and Student Affairs, Bapak Dr. Budiawan, Vice Dean of Faculty of Mathematics and Natural Science, Universitas Indonesia for Research, Venture, and General Administration, Dr. Tito Latifindra, distinguished plenary and invited speakers, faculty managers, head of department, colleague, respectable guests, and participants, ladies and gentlemen. On behalf of the organizing committee, allow me to welcome you all to the 8th International Symposium on Current Progress on Mathematics and Sciences 2022, ISCPMS 2022. Even though almost all countries, including Indonesia, are still facing tough pandemic COVID-19 situation, I hope that this condition doesn't prevent us from sharing the results of our research. Hence, this year, ISCPMS 2022 is held on a hybrid format. In this precious moment, allow me to offer our sincere appreciation to our distinguished speakers who are willing to accept our invitation. We have Professor Muhammad Khairuddin Arowa from Sunway University, Malaysia. We have Professor Peter Barlow from Edinburgh Napier University, UK. Professor Dong Hyun Kim from Chungbuk National University. Professor Shandar Ahmad from Jawaharlal Nehru University, India. Dr. Richard M. Palin from University of Oxford, UK. Dr. Fatwa Firdaus Abdi from HZB Berlin, Germany. Dr. Jong Myung Ha from Korea Institute of Science and Technology, Korea. Dr. Sadika Anwar from University Malaysia Terengganu, Malaysia. And Eric Fentz, PhD from University of Colorado, Boulder, USA. We are warmly welcome you to this annual scientific committee, the 8th ISCPMS conference. With the full awareness on the importance of scientific event like this, the organizing committee continues hosting this conference to provide a convenient platform for students and researchers to submit and present their research work. This also gives the opportunity for the students to exercise their communication skills, presenting the particular subject, responding to the questions from audience, and also deliver their topic in the best way possible. Highlighting the theme of ISCPMS this year, which is Science for Better Life and Environment Post-Pandemic, today events would like to inspire students to keep up the spirit and deliver the best results in innovation and scientific breakthrough. However, with the recent condition of the pandemic, where the number of infected people is still exists around us, this year we try to arrange this conference in a hybrid format to ensure the safety and health of all participants, but still continue to provide the benefits of scientific conference through face-to-face. We believe this will not discourage the participant to be actively involved in a fruitful discussion, exchanging ideas, and sharing the important research findings and make the best of the conference. This year, ISCPMS is attended by 5 distinguished keynote speakers, 4 valuable invited speakers, and 145 parallel speakers. Most participants are from Indonesia, whereas the rest is coming from UK, USA, Germany, Malaysia, and India. As chairperson, I am delighted to witness a satisfying progress of the conference each year. Obviously, pandemic doesn't restrain scientists to keep doing what they do best, producing high quality level innovation and scientific works. On this occasion also, I would like to express our sincere gratitude to the Faculty of Mathematics and Natural Science, Universitas Indonesia, as the major sponsor of this event. Also, this conference sponsored by our valuable sponsor like Luas Birus Utama Company, Global Risk Management Company, Bank Syariah Indonesia, and Saka Energy. My thanks also goes to all ISCPMS 2022 organizing committee who have already given their best effort in preparing the conference. Finally, we welcome you to the conference. I hope you all can enjoy the conference activities online or offline. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Thank you very much, Dr. Dipo, for the message. And now let's come to the second agenda. Allow us to invite Pak Dede Johana, PhD, the Dean of Faculty of Mathematics and Natural Sciences, Universitas Indonesia, to deliver his remarks and also officially open this symposium. Pak Dede, welcome to the stage.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Okay. Good morning, everybody. Thank you for Excellency Vice Rector, Vice Rector Research and Community Engagement with kami, and Professor Muhammad Khairuddin Arwah, Sanwe, Professor Peter Barlow, Professor Dong Ying Kim, Professor Sandar Ahmad, Professor Dr. Richard Ampalin, Dr. Fatwa Firdaus Abdi, and Dr. Jen Myung Ha, dan Dr. Sabika Hanwar, dan Eric Pence, all participants, ladies and gentlemen, thank you. Welcome to ISCPMS. Good morning, everybody. I welcome to EGG International Symposium on Current Progress in Mathematics and Science 2022, which is being held to a hybrid format in Depok City, West Java. As well as now, science helps us to understand many phenomena in the field and also can help us to get the solution for many problems that we are facing in the real world situation. Science is the language that can be used to know about the world. It is enabled to us to engage in the construction of knowledge as well as to use information to achieve the desired ends. It contributes to ensuring the better life environment for us in the past, now and the future. Basic research such as mathematics, physics, chemistry, biology, geography, and geoscience are important key to help us achieving in this goal. Faculty of Mathematics and Natural Science, Universitas Indonesia through ISCPMS so is the commitment to accommodate in the development of science and technology. In this conference, we can share our experience and discuss the further development of many interesting topics in the mathematics, physics, chemistry, biology, geography, and geoscience. Furthermore, in the talk from all speakers would benefit our research community and our students, such as they can experience in the research activity. As the Dean of the Faculty of Mathematics and Natural Science, University Indonesia, I officially open this conference. Hopefully, of all can be have fruitful discussion and conversation. Thank you very much. Assalamualaikum.
Thank you very much, Pak Dede, for the message. And now please allow us to invite Ibu DRG Nurtami, PhD, the Vice Rector of Research and Innovation of Universitas Indonesia, to deliver her remark.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good morning, everybody, and also good evening to those wherever you are, all participants from Indonesia, UK, Korea, India, Malaysia, Germany, USA, and especially for Professor Khairuddin Arwa dan Professor Sabika. Thank you for coming. I would like to welcome all of you to the 8th International Symposium on Current Progress in Mathematics and Sciences 2022, which being held on a hybrid format in Depok City, West Java. So I would like to inform you that UI, or Universitas Indonesia, as one of the largest university, we continue to provide access to scientific developments through research collaborations, implementation of research results, and support for disseminating research results through publications in international journals and also scientific meetings. So we hope that from these activities, the development of science, especially in the field of mathematics and natural science, can be used directly in solving global problems. So in UI nowadays, in our activities through research, innovation, and also community engagements, we aim for academic, social, and also economic impacts from all those activities. So I rely on Faculty of Mathematics and Natural Sciences to deliver most of the outcome of research for this purpose aims. So our consistency and commitment in preparing various facilities for conducting research for lecturers, researchers, and also students. And also we are trying to fulfill the target from our Ministry of Education and Culture, Research and Technology as well, to put UI position in a better world practice. So I congratulate Faculty of Mathematics and Natural Sciences Universitas Indonesia and also the committee who is holding this event, and hopefully all of you can give hopefully this event can give you a maximum benefit for the context of science and also for making global engagements. Thank you very much. Again, congratulations. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you very much, Bu Nurkani, for a meaningful speech. And then, ladies and gentlemen, now it's a photo sessions. So for the Vice Rector, Bu Nurkani, Pak Dede, Dr. Budiawan, and then Dr. Tito Latif, all of the distinguished plenary and invited speaker, Prof. Muhammad Khairuddin Arawa, Dr. Sabikah Anwar, also the faculty managers, head of department, colleagues, and respectable guests, please come forward because we will hold the photo sessions for a moment. Please open the mask for a moment. Please hold it for a moment for a second, because to all of the participants, please also join to come forward to take a group photos. Also, for the online participants, you can turn on your video and please hold it for a moment, because the host also will capture the online participants through the Zoom link. Thank you so much for everyone. Thank you very much, everyone. We will proceed to the next agenda. So, honorable guests, ladies and gentlemen, in a very short moment, we would like to start the first plenary session. Our first keynote speaker is Prof. Muhammad Hairuddin Arawa from Sunway University, Malaysia. He will present the mathematical modeling of carbon dioxide captured states in aqueous amines. Without any further ado, I will invite our moderator first, Dr. Yuni Krisnandi from Department of Chemistry, Faculty of Mathematics and Natural Sciences, to lead the discussion. So, Dr. Yuni, you are kindly requested.
Good morning, everyone. Okay. Assalamualaikum warahmatullahi wabarakatuh. In this beautiful morning, we will have shortly at the University of Nancy, France, before joining Sunway University. His research addresses the fundamental and technical issues related to water, energy, and the environment. He is interested in developing green solvents, and processes for CO2 capture and utilization. Treatment of water and wastewater using novel adsorbents that advance electrochemical process, production of biodiesel, and transformation of its byproducts to value-added chemicals, and providing safe water to communities in remote areas through the application of member the research from the end. Also, he has supervised the completion of 34 PhD and 25 master students, and I'm sure it's still counting. And his research has generated more than 200 articles in ICI ranked journals and over more than 13,000 citations. No wonder his Kinetics currently is 58. And then without further ado, let us warmly welcome Professor Mohammed Kevin Alwar with his speech entitled Mathematical Modeling of CO2 Capture States in Aqueous Amines. Please, Professor Kevin, the time is yours.
Assalamu alaikum. Good morning, good afternoon for those I think online from other time zones, and maybe some they are so evening or night. So good evening to everyone. Thank you for the introduction. I'm very happy to be here because this is going to be a conference that I will never forget. Why? Because it's the first conference that I participate partially face-to-face due to the pandemic. So we have passed through more than 2 years of very difficult time everywhere, and we lost also the habits of traveling. I left Malaysia and I forgot all my name cards at home because we used to just only online. So I'm happy to be here. I would like to thank the organizer for inviting me to this conference, and congratulate also to the organizer to organize it in this dual modes, which is not easy. I appreciate that. And this is how I came here also, is through collaboration, because I'm collaborating with Dr. Munawar Khalil. He's not here with us now. Now I think he's in US, enjoying the stay there. And through his our collaboration, so I got to get in touch, contacted with the organizer of this conference. That's how I came here. So I'm not a mathematician, but the reason why I accepted this talk because I wanted to support our friends here, the organizer, and also because I'm looking also to extend my network. With the University of Indonesia, I have collaboration with the Faculty of Science, Dr. Munawar Khalil, and also with the Faculty of Engineering. We started some work together with the University of Toulouse, France, on biomass valorization. And my work basically is chemical engineering background, and we use a lot of mathematical modeling. So today I'm going to share with you what we use in modeling that help us in our research, with the objective, hopefully, to extend and to have more collaboration with the Department of Mathematics here, because through multidisciplinary research, I think we can tackle the grand challenges. And the CO2 is one of the grand problems facing humanity and life on Earth. So I will talk about that later. So I'm now with Sunway University for 5 years, as well as Lancaster University. I have double position, 20% with Lancaster, 80% with Sunway University. But I have been with the University of Malaya for 23 years. last now 5 years with Sunway University, and it means that I'm not young, and that's why I explain why I have a lot of citation, because I have been I did my PhD in France in 1992, so that explains why I have a high citation. So it's not because of course it's good work produced. So today I will present on the mathematical modeling of CO2 capture states in aqueous amine solution. Since we started early, I think it's supposed to be 10 o'clock, so I have more time. And I prepared some slides and video to show, promote is to make our Sunway University known, because it's a small university, young university, and many of you maybe you don't know about Sunway University, and I think many of you know about Sunway Resort, maybe, and Sunway Pyramid, and Sunway what's called the theme park. So these are all under one group, and we are at the same group as Sunway University. Let me check. We have a video here about Sunway, about 3-minute video.
Conscience, a state of awareness with a feeling. Of obligation to do the right thing and to do the thing right. At Sunway University, we aspire to cultivate a sense of collective responsibility within our community of learners, educators, researchers, and inspirational leaders. Nurturing a holistic education whilst promoting a planetary health mindset. Through education, practice, and experience. At Sunway University, we encourage a heightened sense of awareness and responsibility of the world we live in. Our actions, our desires, the outcomes, and the results. We practice what we preach. By doing it physically, harnessing renewable energy, conserving the planet, taking vital resources seriously, and delivering it to all. Creating solutions, planning for a greener future, identifying sustainable solutions and working together to achieve them. By instilling a culture of conscience in our campus, our community, our city, and our collaboration of countries. To be that little voice of positive influence in all who pass through these halls of enlightenment. To give our beloved planet and future generations the greatest gift of all. The gift of a sustainable future, the gift of eternal life. To do the right thing and to do the thing right. Sunway University, truly a class above.
Okay, so that's the video to give an idea. So the thing that we have to maybe take from there is we have to do things right. And I hope everybody can do things right, especially researcher students are the future. And I hope we can save our planet, because planetary health is one of the niche area that the university is embarking on. Planetary health englobes everything. When you have planetary, a healthy planet, you have healthy people, you have healthy cities, healthy animals, etc. So this is basically the university, this university building. And this is Samay Lagoon, one of the largest, I think. So it's only 5 minutes walk to the university. And this view is basically from Samay Resort. Also, we have Sunway Pyramid there, one of the biggest shopping complexes in Malaysia. So it's a very vibrant city. It's we are considered smart city. And there are 3 universities in the city. We have Sunway University, we have Taylor University, and also Monash University, Malaysia. Monash University is to be owned by the by Sunway Group, about 51%, but I think lately they sold some parts of their almost separated now from Sunway Group. So this is a few quick facts about the university. So the number of students is about 8,300. It was established as university in 2011. Before it was Sunway College. So it's a very young university, but it's also a very dynamic university. And the foundation started investing in research about 6 years ago. We developed a number of state-of-the-art facilities, centers, etc. So we have 83 academic programs, 7 schools. One of them is School of Engineering and Technology, where I am attached. 20 research centers, 5 research clusters. I am a leader of one of the cluster and the head of one of the research centers, and as well the associate dean for research at the School of Engineering. So I have too many hats. And it's not for-profit private university. It's really not profit because it's under the foundation, the Jeffrey Cha Foundation, and all the money collected from fees at undergraduate level are re-injected to support research, to support scholarships. We give a lot of scholarships, PhD scholarships. It's very one of the, for this year, for example, we investigate about 50 studentship scholarships, this for PhD student, which come with a stipend of 3,000 ringgit per month. Stipend, one of the highest in Malaysia, plus full fee waiver, and also 10,000 ringgit per year to support the research of the student, which comes to more than 150,000 per student for 3 years. And this by private university. The reason is because we it's under the group, and our chairman, Jeffrey Cha, believes that education should is important, and even if the university runs in negative, it doesn't matter, because there's the group, there's a big group that support the university. We are also similar at University of Indonesia, looking at ranking. We are pushing a lot on ranking. These are different ranks. We are also involved in UI green metrics. We have 280. And the university had adopted the Sustainable Development Goals as strategic impacts to shape our research. When you go there, you can see we have a lot on sustainability goals, SDGs 17. So the pillars of the Summer University is holistic education, focus on of education and research. It's research and University, development, research at the safe, multidisciplinary, and also entrepreneurial. These are some of the relevant collaboration that the university has. And now the university is establishing a medical school with the collaboration with Cambridge. So because our chairman wants the university to be highly ranked and without engineering, medical and law, it is very difficult. But of course, for law, to have a law faculty maybe is impossible because it's controlled, regulated by the Malaysian government. But for the medical, the group were able to get the license. So we'll have a medical school soon. These are the different centers. So my center is Research Center about the Untitled Capture and Utilization. So these are specs. We are, as I mentioned, a lot looking at sustainable development goals. And all our research normally is mapped to the 17 goals, as well as the Malaysian 1010 IST framework. It's a small university, but it has a number of highly cited researchers, and it is recruiting more highly cited researchers. And our president is one of them. This is the president of the president of the university. So he's a highly cited researcher, well-known scientist. It means that the university is serious about research. I put it someone who supports a lot of research, and since he started as president, you can see a lot of investment in research coming here. And many international staff we have. These are some of the very important area, and I'm proud that this collaboration is with my center, research center, CO2 Capture, and the foundation is supporting 3 years contract with an MIT group. And today I'm going to share with you some of the work that we do with them and some of the results that we achieved so far. So it's the first one type because it's a research collaboration, it's an agreement. We plan, I think, to have this collaboration sustained in the future. This is the publication. Sorry, there's comparison with other, we think our other private competitors, but Sunway, as you can see, has been developing a lot in terms of output. These are scopes and text of publication, and we are looking at around 1,000 for this year. The total number of staff is about 400, so we're looking at more than 2.5 publications per year by staff, with a target in 2025 to be more than 3 publications per year per staff. So this is the School of Engineering and Technology. It's one of the biggest schools in the university. We have more than 1,400 students, 9 academic programs, 2 academic departments, 5 research centers and a group, and we have 56 staff, including admin. So academic staff is about 40, and in 2021, we published more than 400 Scopus publication, which equivalent to 10 publication per staff, academic staff, which is something even higher than research universities in Malaysia. So this is the school is one of the driving force for the. We have some staff for producing the paper. These are in material, especially physics. We have a very highly productive staff. We have 2 academic departments, computing and Department of Engineering. The Department of Engineering just started last year. It's a new department. These are the 5 centers that we have. Research Center for Applied Physics, Center for Research Carbon CO2 Capture and Utilization, Research Center for Human-Machine Collaboration, Research Center for Nanomaterial. So applied physics, the nanomaterial tools at the center, and the graphene material that produces the highest number of applications in the school. Okay? Later come my center, and this is because different fields there is different way. The outcome is different. So these are the different areas, and we are very open for collaboration, and not only I go to talk about, but other areas. Maybe later we can share, I think, the slides. If you identify any fields of interest, you can contact me as associate dean. I wanted to show this on our engineering degrees because we have two programs. Is the Bachelor of Chemical Engineering, started only in March this year, and Bachelor of Electrical and Electronic Engineering. But what is important here and very attractive, students, when they graduate, they will get a bachelor degree from Malaysia, which is recognized by BEM. Hence, it is internationally recognized through Washington Accord. But the interesting thing is that they will get also another certificate from Lancaster as a Master of Engineering. So Lancaster University recognizes our program as a master level as compared to UK master level. Now, of course, the BEM, the Board of Engineering Malaysia, they don't recognize a master for 4 years. 4 years will be given as special level. Without extra means fees. So the same fees, the student one from Sunway. And Lancaster is one of the collaborators at our university for more than 15 years since it was a college, and we have double degrees of many of the programs. And this is something very attractive for students. And when I mentioned to our president that I'm going to use his, because the slides that present at the university, our president's slides. So he mentioned to me, try to promote the programs for Indonesia because now universities are working hard to be able to get students from Indonesia directly there. So it will be possible for Indonesian students to come to get these activities. Okay, something lost there. Yeah. Okay. It's okay, we have time. So after this, I will present about my sector. Then I'll start. Okay. So I wanted to take more time to show Samuel because I think it's not known. This I think it's good to know about it. So when you travel to to Malaysia, Sunway City is not very far from KL. It's not very far from KLIA, so if you drop by, so you can come and visit us. Okay, let's wait for the technical. So my research center is on CO2 capture and utilization. It was established in 2018. So I joined the university in July 2017, and for the reason I joined because of the attractive arrangement with Lancaster, as well as the promise to develop my center because after many years of research, it is through the center, developing my own center, I can contribute better, I think, to the community. And then I was happy, I think, that the center was approved. And within 9 months, we transformed classrooms to labs. And, my work is more chemical engineering rigs, so it's not easy. But things go very fast with Sunway University. And within 9 months, after January 2018, the center was already operating. So currently, I have one senior research fellow, one research fellow, and one lab executive. And we have also members and their projects. So I have one research fellow from Bangladesh and two RAs. Both of them, they are now our student, PhD student. They are the PhD in Sustainability Science and Technology in our school. Now the team with a few projects, we have other RAs, so about more than 10 members, including RAs, students, and so these are our focus area. Maybe we work on developing the new solvents and solvent formulation. We work a lot on amines and deep eutectic solvent, ionic liquids, adsorbent from biomass. And you can see we have a lot of collaboration, because this is basically addressing the grand challenge. Only through collaboration, through multidisciplinary research, that we can achieve something. We work by ourselves as a group, our one team or one member or industry would not be possible. And I have collaboration with MIT, with the University of Indonesia on the same topic on the electrochemical. And I have a lot of work with UM because of my history with UM. So I'm still a PhD student there in UM. And we are still exploring, and hopefully we can, after this conference, I got also some collaboration with the mathematical department here, because we need a lot of maths in our research. So these are some of the areas. It's a small lab, but it's focused on CO2 capture, studies, and utilization. Okay, so coming here to my talk. Okay, and so today I would like to share with you some of the work first to show you what we are doing and what type of mathematical tools that we need, looking for possibility of collaboration with our friends from mathematical department. What is important. Just now, I think the dean mentioned to me whether we can take this conference to Sunway next year. I think that would be a very good idea. So, because we have a mathematical maths school and mathematical school there, so we can combine. I think our school, mathematical school, and our school here, we can organize. So we may discuss this later, but it's something interesting. We can have it as an outcome of this my participation here. Because this year I'm organizing the CO2 conference in December, but next year our conference will be 2 years, so I'm not organizing a conference next year, but it will be this one that would be very good. I think we can discuss later. So why CO2 capture and utilization? Of course, when anybody talk about CO2, the first thing come to the mind is environment, climate change, etc. But not only that. And always I use this slide everywhere because I have to show to people who are not very maybe familiar from the term, from technology. CO2 capture is important not only for the environment, but also in oil and gas. You know, CO2 is always associated with natural gas, and the natural gas, when extracted, can contain 20% of CO2 and even more than that. And it cannot be used directly with the CO2 because CO2 is corrosive. So transportation is very, very difficult and it's costly. Value of the gas and to make it easy to transport and to use it. Biogas is another example where you need to remove CO2 also if you want to upgrade it to biomethane. because it can contain up to 40% of CO2 and depends on the source of the biogas. Of course, it has also H2S, but CO2 is important there. CO2 also is important in some industry, the methanol conversion, for example, production, because if you keep CO2 in the synthetic gas, it can corrode for equipment, can also degrade the catalyst. Furthermore, in CO2 utilization, CO2 has a lot of commercial application and usage. So it's not only bad for environment, but it has a value also as a supercritical fluid for some green extractions techniques. It can be used in enhanced oil recovery. It can be used, of course, we know it is used, dry ice is CO2 basically at the solid state. Is used in, for example, Baskin Robbins, when you go and buy ice cream, they put the dry ice there, so this uses. So it is used also in other industry, and there's a lot of research now looking how to convert CO2. CO2 is a very stable molecule, but it can be reduced to form produce CO, which is a compound of synthetic gas, or it can be converted to other chemicals through catalysis. So this is a lot of development now and research to that direction of using CO2. So, so it has it impacts a number of sustainable development goals, and also only through collaboration, where we can also address the SDG 17, which is partnership for the goals. So working on CO2, I tell my students and tell my friends that it is something for long, it will be here for a long time. Not even if we solve the climate change, if you solve the issue of climate, still CO2 has to be removed for other reasons. And if you remember, during the Mars mission of NASA, they managed to use the CO2 in the atmosphere of Mars to produce oxygen. So it means that by working on CO2, of course, we are saving life on Earth, but we can create life also in other planets. So it will be there for centuries. Of course, global warming is the main issue, and this is because of the increase in the Earth's surface, and it is well established that CO2 is one of the major contributors. Because there's other greenhouse gases, methane, nitrous oxide, and other industrial gases, but because molecule to molecule, the impact of CO2 is much higher. The impact of CO2 is not very high compared to the fluorinated gases. But because of the emission of CO2 from the industry, from the transport, are very high, the overall contribution of CO2 can go beyond 75% on the global. So it's very important to try to reduce the emission of CO2, but also to capture CO2 from the atmosphere, for example, and utilize it. Because this is a very famous, I think, graph shows the concentration of CO2 in the atmosphere for many years, thousands of years, and you can see that although there is a cycle, because some who are against the climate change and against the CO2 involvement, they tell you that there is a cycle, there's an increase and decrease of the CO2. Yes, there's a cycle, natural cycle, but you can see the whatever cycle, all these years, the value of CO2 in the atmosphere was less than 300 ppm. And after the Industrial Revolution in the 1950, it peaked, and now it is more than 410, maybe even is it still increasing? So it means that we are not in the natural And we know the nature is very, very sensitive. We say it's just only 100 ppm, 100 part per million. It's very, very little, but that very little can affect a lot. You know, small change in the pH of a river can kill the fish. You know, it's not a question of is a lot or not a lot. So we are very, very far from the natural or the baseline concentration of CO2. So we have to do something in order to utilize or use this CO2 to reduce that. Maybe we'll not be able to come down to the 300 level, but at least to reduce, because we have been now experiencing the effect of the impact of the climate change, the typhoons, the floods, drought. It is happening more frequently, and it becoming more severe. And I think we cannot deny that. We have been seeing that. Even I have been in Malaysia for 30 years, 29 years. Okay, and we can see the different temperatures. That is even the weather. I know we don't know when is it the monsoon. The monsoon, and it's very worrying. And CO2 can be used in a broad range of application, direct use or through conversion. So it is very, very important to capture CO2 from, of course, from the emissions and also from the atmosphere. So there's a lot of work going now to try to capture CO2 from the atmosphere, because I think that's the more important technology that can maybe help reduce CO2 in the atmosphere, because even we are reducing the emission at the source, and because of the climate change, there's more forest fires. Forest fires burn the trees in few weeks, and these trees have stored CO2 for maybe thousands of years, can burn them. So, and these are becoming everywhere and more frequent. Algeria, Tunisia, US, everywhere. I think the only solution is basically to be able to remove CO2 from the atmosphere. But it's very, very challenging, because it's very costly now. Now it's costly, but with innovation, I think we can go be able to develop and to make it more economical. So the benchmark technology that exists now for CO2 capture is Aqueous amine, based on absorption and desorption process. Why it is the benchmark? Because as I mentioned to you, CO2 is important to be removed from oil, from gas, natural gas. So the technology for CO2 removal natural gas has been there for more than a century. It's very old technology, well established. So it is basically the benchmark technology now, and it is based on the principle two columns. This is a very schematic diagram. One column where we absorb the CO2 using amine solutions. Amine aqueous solution, they are basic. CO2 is a acid gas, so they react, and CO2 is fixed in the solution, and then the reaction is reversible by hitting the solution saturated with CO2, so you can take back the CO2. So we have another column we call the regeneration, where the captured CO2 can be produced as pure, and the lean solution can be recycled. So this is a typical process used in oil and gas, and is the benchmark, because amines are very powerful materials to absorb CO2. There are different types of amines. Primary amines, normally they have methyl group or alkylamine group, and two hydrogens. We have secondary amines and tertiary amines. So it depends. I think some here are from chemistry, so you will know based on the number of hydrogens available. So these are MEA is basically the most established amine, and they have different reaction characteristics. Primary, secondary amine normally react fast with CO2, but they have lower capacity than tertiary amines. Tertiary amines react slow, but they are used at different application. Why is important to know about the rate of the reaction? Because the design of the column depends a lot of how fast CO2 reacts with the amine. So as a rule of thumb, if the reaction is fast, we will have smaller columns, more easy to control and cheaper to fabricate, and the process is more economical. But tertiary amines, they can react very selectively with H2S. If you have a mixture of H2S and CO2, tertiary amines will be important to remove first H2S. And also they react, they're easy to regenerate compared to primary and secondary amines. There are also other types of amines. The sterically handed amines, normally they are primary or secondary amine with the steric hindrance. So they will have the properties of primary amines and secondary amines in terms of rate of reaction, and they have the properties of tertiary amines in terms of capacity. And there are some activators like piperazine. We mix with other amines to make the reaction more fast. And amine blends, I mean mixture of MEA, MDA, DA, MDA, and this is to take advantage of both amines. So there's a lot of options, and of course if you add recent research on ionic liquids and deep eutectic solvents, so these other also option, and things become more complex and complicated. So what is the fundamental concept in the CO2 capture by aqueous amines is that you have the CO2 at the gas phase, and through a mass transfer, the CO2 will be transferred to the liquid phase. And when it is in contact with the liquid which contains the amine, so a series of reactions take place. So if it is tertiary amine, so it will be acid-base reaction, so you will have only carbonate and bicarbonate. But if it is a secondary or primary amine, you will have a carbamate which is formed. This is very, very important that you will see how. So the CO2 will be fixed in the liquid as non-volatile ions or species. Okay? So these are the captured states of CO2 when it is in contact with amine solution. And in order for the system to be applied in industry, the solvent has to be regenerated. And that's why when we develop solvents, like green solvent, new solvent, we look at the reversibility of the reaction. And the amines, they can be reversed easy. So the regeneration is just by heating. You can regenerate CO2. You can convert back to the carbamate, bicarbonate, and carbonate to CO2. And because of this regeneration, so we can use it in industry, because you cannot just use every time the solvent is very, very, very expensive. So you have to regenerate it. So it's one of the important aspects when you're developing solvents, which is the regeneration must be more economical. Because the main cost of the overall capture process is on the regeneration, because it involves high temperatures. Okay? So why it is important to do speciation? So speciation in chemistry means that we determine the composition of the CO2 capture states. What are the composition of CO3 2 minus, carbonate, bicarbonate, carbamate. So by definition, or by in chemistry we call it speciation. So we not know how much CO2 has been captured, but what are the concentration in form of carbamate, which concentration of CO2 in form of carbonate, which concentration in form of bicarbonate. Why it is important? Because it has first, in terms of thermodynamics, determination of equilibrium constant. Kinetics is important to know, because when we want to compute the kinetics of the reaction, it is important to know what are the reaction mechanism, the intermediates, etc. Corrosivity and degradation evaluation. especially speciation at high temperature, to know what are the components responsible for corrosion and the degradation products. But it's very, very important also in validation of multiple models that I will present later, and the reaction mechanism for the conversion of CO2. Different species of CO2, can be converted to different components. For example, the carbamate. So this is basically our work with MIT, working more on this process. So it can, the carbamate can be converted to CO. So CO is a compound of synthesis gas. So CO plus hydrogen, and the industry of the synthesis gas is already established. So if you are able to convert carbamate to CO, and you add the H2 that can come from some green processes, from water electrolysis, for example, so you can convert basically CO2 to any components based on the chemistry of synthesis gas. So this is basically the work that we are collaborating with MIT. They are more on the electrochemical conversion. We are working more on the capturing the solvents. We are developing new electrolyte systems, etc. So it's a complementary research. If you have bicarbonate can be transformed to formate, for example. So different species can be transformed by different processes and give different products. So that's why it's important to know what is the status of the CO2 when it is captured. So that's the importance, and why we are working on that, especially in terms of modeling. The models will help us to predict, and the experiment help us to validate the models, to help us also to optimize. If we are more interested to carbamate, so we have to look at ways how we maximize the carbonate in the system. If you are looking at to use the bicarbonate as the transformation, so we need to maximize the bicarbonate in the system. Okay, so if you have the system, you have bicarbonate high and carbamate high, and you are interested only on the carbonate, means that you are losing some of the CO2 in terms of bicarbonate. So this is the idea overall, the concept of why it's important to do the speciation. And so these are the reactions. So the speciation basically is to model the reaction taking place and to transform it to a mathematical model and solve it to get the concentration. So for primary and secondary amines, so we have the dissociation of protonated amine, dissociation of carbon dioxide to bicarbonate, dissociation of bicarbonate to carbonate, formation of carbamate, so this is how it is written, and water dissociation. And these are the corresponding equilibrium constant in terms of activities of the species involved. So the reaction with tertiary and secondary handed amines, so we don't have the carbamate, but we have the other reactions, and these are the equilibrium constant, of course with the water dissociation constant, as we are using water as the solvent. But if you are, there's also work a lot on non-aqueous solution. So when you have a non-aqueous solution, of course the chemistry change. So this is what I'm talking here is mainly on the aqueous solution. So the thermodynamical framework should have 4 basic or fundamental concepts. One is, of course, the gas phase equilibrium, the CO2 in the gas phase equilibrium with the CO2 in the liquid phase, and this is normally governed by the Henry law through the Henry constant, and the liquid phase equilibrium, where it is governed by the dissociation constant of the different acid species, or in addition, a carbamate formation constant if you have primary or secondary amines. And of course, you should have the amine mole balance. And the electroneutrality, because you're looking at is an electrolyte system, aqueous. So the solution is neutral, with the concentration of positive charge are equal to the negative charge. So you combine this, you transform into equations, then you have a system of equation with a number of unknown, and normally the number of unknown is the same as the number of equation, then you can solve it. So once you have all the concentration, you can calculate all the CO2 loading and concentration could be calculated. And of course, we do experiments to validate the model. And from the model, we are able also to optimize and see how we can maximize the concentration of the species that we are interested in. So this is an example, I think, the equation, the Ka values, with when you transform the activity coefficient with the concentration, and these are the activity coefficients. So the main challenge is basically to have the activity coefficients and to have the different constant, especially the carbamate constant. You are looking at primary or secondary amine, and these are normally the challenge that we face when we develop, especially new solvent, and we don't have the data for the constant there. There's some other more work to be done, I think, to develop this. So at the end, you can see you have 8 unknown, because the gamma we can calculate through some models. I think the Dubai Hotel model or Pizza model or electrolyte and ITL model, and it can be calculated and related to the concentration or the ionic strength of the solution. So we have 8, and we need 8 equations. So we have 5 here. Then if we add gas phase equilibrium, these are the total amine balance, and this is the electroneutrality. So at the end, we have 8 equations with 8 unknowns. So theoretically, could be solved, and we can calculate the total CO2 once we have all the concentration. So what we use, because we are, as I said, we are not mathematicians, so we cannot maybe solve it, the system. The tools to solve the system, or we can use in our work, we use MATCAT. It's very easy to use, so we can solve a system of nonlinear multiple equation with multiple unknown. So that's how we use that. Of course, there's a lot of other techniques and other models. So this is an example with this work have been done when I was in UM. So type of, we can use the electrolyte and RTL model. So the model have to describe well the activity coefficient. It must be very thermodynamical based model, and this model is incorporated in SPM Plus, so it's easy. It's very, very complicated model. It requires a lot of parameters, etc. And this is a type of speciation for tertiary amine. MDA is the tertiary amine, so there is no carbamate. And these are the this is the protonated amine. As you increase the loading, you see the mole of CO2 by mole of pH. When you increase the loading, the pH of solution is decreasing on the other side. So you have more protonated amine. You have more bicarbonate. These are the major compounds of bicarbonate, and this is the protonated amine increasing, and the free amine is reducing. And this is the CO3, so very, very low species. So you can see in tertiary amines you cannot convert bicarbonate because it doesn't exist. It doesn't form. The tertiary amine doesn't have the extra hydrogen to form the carbamate. For secondary amine, the DA, the diethanolamine, so you can see the carbamate, and you can see that it is increasing, but it decreases if the loading exceeds 0.5, and this is basically the reverse reaction, the hydrolysis of the carbamate. So it means that we are interested to convert carbamate, you should be in this where there's high concentration of carbonate. If you are looking at low loading or even high loading, you're adding more CO2, but the CO2 is lost as bicarbonate. So if you are interested in carbonate, so this is just to show you why it is important to know the species concentration. So in our work, one of the focus area with our MIT collaborator is looking at speciation in MEA, H2O, CO2, and electrolyte system. So I'll say why we want to use some electrolyte system, because in the process of the conversion of of the carbonate, it's an electrochemical process. So we need to add some electrolytes to make the process more efficient. So the work that I'm going to present now is basically one of the show how we work together. There in US, we are in some way in Malaysia, but we can work together, complement each other. So what we are doing here in Sunway, basically we are looking at using MatCat to develop the concentration of different species. And other side, they are doing, we give them same conditions. For example, we want this pH, this concentration of amine, this concentration of electrolyte, and they do the NMR analysis. They're very, very fast there. I don't know, one day, first time I work with American, they experiment, they can produce very, very fast, especially using NMR. We can use NMR in some way, but the queue is very long, and I don't know how they do it there so fast. Our collaborator, Dr. Beta, she came 2 weeks ago. She visited Sunway, and I maybe next year, because I want to know how they work basically so fast in terms of experimental. It's really the access to the high, because NMR you cannot have like in every lab one. So anyway, so it's very interesting experience for us, for our researcher and the researchers also. So this is a very good example of what we need in collaboration. Basically, that the expertise should be complement each other, not doing the same thing, but working on the same problem, but having different expertise from different areas that combine together. That will be very good synergy and better outcome at the end. So mainly the work is done by Dr. Graham, who is a postdoc there. In our work, we didn't want to use, there's a lot of models, and most of the models, they need data regression and not, the only model on activity coefficient that it is derived from theory is the Dubai-Huckel equation, this equation. Then the Pritzker maybe for high ionic strength system. So we wanted to use extend Dubai-Huckel equation, although it has limitation in terms of but we can see that even using this equation, we are able to predict correctly, I think, the species. And this is an example. So the MatCat is very easy to use. You just write your equation, initial. These are the different key values, and so we have only 7. Why? Because we fix the pH. So when you fix the pH, one unknown is removed, so it will become the input. So we have only 7 equations and 7 unknown because we fix the pH, and the pH is given to the MIT group. We want to they prepare the solution at this pH, and then they do the NMR. Okay, and so it's very easy to use, and normally we do iteration. So we do the first calculation. Taking all the activity coefficient equal to 1, we estimate the ionic strength, we use the ionic strength to calculate the activity coefficient, and we redo until maybe 2 or 3 iterations, then we get the final concentration. So this is an example of the carbamate versus pH in 2 molar at 25 degree using the extended Dubai-Huckel model. So we can see that we are having the maximum, as of course shown previously with SPM+, which is around this pH. Okay, and we have 2 molar, so it's the only 0.8 moles of the amine is in form of carbamate. So the others is protonated amine. This and the CO2 is bicarbonate. So not all the amine is in the form of carbonate. So very important to know this maximum, where if you are interested is in convert to the carbamate. So this is the example of the comparison. So the data, the experimental data are given by MIT. So these are, and this is the calculated. So it's very good what we call concordance between the two. And the maximum, as I mentioned, is only 0.8, and the ratio less than 0.5. Can we go beyond this value? So how do we optimize this? So of course we are researcher, and if we understand well the thermodynamics of the process, the chemistry, you are able to know how we can go beyond that. Because this is thermodynamically limited. Huh? So how we go beyond the thermodynamic? Of course, we were managed to go further than that. I'm not putting what electrolyte we use here, but soon I think we're working on my school together with them. So hopefully by end of this year we'll have the publication very, very good journal. So we are able to go beyond. This is the MEA. So this is with one electrolyte, A1. This is another electrolyte. So we can enhance the concentration of the maximum of the carbamate to almost 1.4 molar. And it is shown and verified experimentally at MIT and verified by our model, which is very give us confidence. I think we can use the model basically to optimize. And this is very, very important because we are now for this, the history of using the carbamate to form CO comes from another group, I think, research, and it is very, very good research. And now we are able to try to verify the mechanism. Is it really the carbonate or the bicarbonate or mix of them working? So through this, we are trying to explain better the mechanism of what is happening. Because if it is the carbamate, so if we do the electrochemical process here, we should have better conversion to CO, etc. So this is, we have another student, PhD student there in MIT. She's working on that. So, but if this system doesn't give a better CO production, so means there's something wrong with the mechanism, or we have to look what is the best mechanism. So it's very interesting, very fascinating. And this is, of course, the bicarbonate, also compared with the experimental values. And this is the MEA. And of course, in our lab, especially when I was in one, we developed a very simple, of course, NMR, not everywhere is available, but we can have also simple techniques to estimate the concentration of carbamate and bicarbonate, but not, because it is simple, it has a very limited range of validity. So if you are between if your solution has a pH between 8 to 10, you can neglect some of the reaction. Because 8 to 10, if your carbonate pKa is around 11, so you can say that 10% is already in form of carbonate. And between 8 to 10 also, you can neglect the dissociation of CO2 to bicarbonate. And we can reduce the equation to only 4 if we add the Amines the neutralization with the base. So when you neutralize your solution with the base, so the base will only react with the acid component with the protonated amine, the bicarbonate. So you have 4 equations with 4 unknown, and it can be solved easily to get the carbamate concentration. So this is only valid in a certain range of pH because we can make some assumptions. So we are also now setting up the system and the experimental work with the PhD student. One of them I show you in our team. So she's going to work on this area as well as developing the kinetics with electrolytes. Kinetics are important, especially for chemical engineers. If you want to scale up and design the reactors, the kinetics, because most in the industry application reaction doesn't go for equilibrium. All are kinetic limited. So I mean your design of reactor, design of columns, absorption columns are based on kinetics and rate. All the residence time species inside the vessel. So in conclusion, I spoke a lot, I think more than the time given to me. So mathematical modeling based on thermodynamic sound framework permits to predict accurately the concentration of CO2 capture states. Of course, we have shown our work with the MIT project that we had specific electrolytes were possible, I think, to increase the concentration of carbamate beyond the thermodynamical limit. Of course, we need to evaluate more on the effect of the electrolytes on the kinetics and the absorption process as well as electrochemical conversion. And you can see, I think, from now how we need mathematical modeling because now we are using tools like the black box equation, but I think there's a lot of work, and especially in developing of artificial intelligence or neural networks, deep learning, etc. So while other can help, I think, although maybe it will be difficult to get the species concentration because need thermodynamical model, but at least maybe evaluate the capacity of absorption, to predict maybe the kinetics or so. So there's a lot to be done there. We are starting some work with some colleagues extern on this. We are interested also to explore that from other groups. So with this, thank you very much. And if you have any questions now, I'll try to answer.
Thank you very much. Give round applause to Khaireddin. And now it's come to question and answer. Please, if the participants here in this room, you want to ask directly, just raise your hand and then, yeah, you can have the question directly. So it is very, very interesting. Yes, yeah, because I also personally work with my group for CO2 storage and conversion. Storage is, I don't say it's easier, but conversion is very, very challenging. Yeah, but
Okay, we are organizing a conference in December.
Yeah.
That is fully online. I will send you
yes, please.
the
Yes.
speaker. I think we're having Dr. Munawar as one of our panel speakers.
Okay.
But if you are, you have, we can invite you as a speaker.
No, I'm still learning about that. Yes, yeah, but
No, don't worry. I think all of us still learning. At 60 years old, just turned 60. So we still learn. But now our learning rate is very slow. That's history.
yes. Okay, anybody here? We still have plenty of times, yeah. But if not, oh, okay.
Interested presentation, but I'm so curious about your this. Yeah. First, about based on chemicals, chemistry. I mean, it's about you use carbamate as you know the amines. So there is the tertiary, primary, secondary, and tertiary. But in this case, you use a tertiary amine derivative, right? Not the first or the second amine in this case. The tertiary amine, right?
We use MEA in our words.
Amine
MEA
A.
is the monoethanol amine.
The monoethylamine.
It's
Primary. Oh, okay. Also, I'm mistaken. So that's why I'm curious why.
Yeah.
This one is because
Tertiary
it's not-
amines.
it's
Maybe I can show you the
okay.
why.
Can you more
why
explain
it
about that?
doesn't form? Huh?
Yeah. Okay.
Equation. Okay, you see this is the equation of the carbamate formation.
Mm-hmm.
So the amine needs to have a hydrogen at least
Yeah, that's right.
to do this here. So the tertiary amine doesn't have this hydrogen,
Mm-hmm.
so they don't form carbamate.
Oh.
Sterically amines, the primary.
Mhm.
I mean the hydrogen is there, but it is these are very bulk because it's the reaction is SN2
Yeah.
reaction. So nucleophilic
Yeah.
reaction.
Right. Yeah.
So if it is these are bulk, so the reaction is hindered and it doesn't. In fact, if you look, the mechanism it forms, but it's not stable.
Mhm.
That's why they they react very fast
Right.
because the carbamate is formed in the intermediate veteran is formed,
Right.
but it is very fast.
Yeah.
It's not as stable as primary and secondary
Yeah.
amines.
Okay. Thank you very much. You was
Okay.
just clear. And the other question about the data where you presented about the between carbamate and pH. Yeah.
Yes.
Just based on your data, there's on pH 9. I think you
Yes.
can. What is the happen after when we use I mean more than pH? There's data 10, right?
Yes.
So what kind of the product in this case?
So if you combine, basically, we can combine these two equations,
Yeah.
and then you will have at the end three equations. This one, and this one. You can get the overall
Okay.
equation. You will see that it will be a stoichiometry of
Mhm.
0.5, and because at higher pH,
Mhm.
the carbamate can reverse back to
Mhm.
bicarbonate. Then you have more bicarbonate.
Okay.
So you absorb more CO2, but it is formed more
Okay.
bicarbonate than carbamate. So it's like
Okay.
competing reactions. Basically.
Oh, okay. And how about if the lower than?
Lower pH,
Yeah.
lower pH because the bicarbonate is still not
Not right.
not high,
Yeah.
but that's the reaction because it's
Okay.
the reaction of that's why it's increasing.
Yeah.
The carbamate is increasing, but
Yeah.
the carbonate increasing by very low.
Very low.
So if you look at is well shown in the okay, you see here the bicarbonate is only starts at this. So
Mhm.
this is lower pH. So
Yeah.
the pH normally decrease on the side. So the
Okay.
mainly initially is you have your carbamate is the main. Then the bicarbonate starts slowly,
Mm.
and here you have more bicarbonate there.
So that means
So this is very good picture and shows where if you are interested to convert bicarbonate,
Mhm.
so you have to be in this area. If you are working here and on bicarbonate, it means you are losing a lot. So better maybe you have to go back as tertiary amine, where you don't
Okay.
have the carbamate, or if you are using the primary or secondary amine, so you have to know where to do this pH.
Mhm. Okay. Thank you very much.
Okay, welcome. And yeah, we still have maybe one question from maybe online participants. If there are any questions, then
And you
Can
have
al-
my email address, I think. you have anything, you can email me
Yeah.
later. It doesn't matter if you are shy,
Yeah.
there.
Oh,
Yes.
there is any or okay,
yeah.
Pak Dipo. Yeah,
Yes, chairman. Okay.
the chairman is the mathematicians.
Yeah.
Yeah. So yeah.
Okay.
Okay, yeah, this is interesting that how mathematics can contribute in your work. I'm sorry if my question is not so chemistry.
No, it's
So,
okay, it's okay.
yeah,
It's good.
in your aims is to fit is it true that you want to fit the data and the direct calculation of the graphic?
Of
Conceptual?
course, the best way to have a model that can fit to the data, we do what we do, the regression.
Oh,
So in
okay.
this work, we didn't want to do data regression.
Oh, okay.
Why we wanted just to use purely thermodynamical model,
Oh, okay.
activity coefficient, and see how it performs.
Oh,
If we are happy, I think with the trend, if we can see that the pH, maximum pH,
mhm,
is almost similar,
yeah.
and the maximum value of carbonate is similar, for us is good. But of course, we can improve the model by doing regression. That's the issue of the majority of models that are you use a very sophisticated model like electrolyte and RTM model, but at the end you do data regression to get the parameters. So you use that because if you do regression, you get the parameters that fits the
Yeah.
experimental data. Of course, the model can,
Yeah,
work
Yes.
basically. But this is a model without doing any regression.
Oh,
We
okay.
use the K value from the literature,
Mhm.
constants, carbonate constant K1, K2R, and we use activity coefficient into by calculation as it is without any regression. So and gives very good, I think.
Yeah.
estimation.
So in your
But we are also interested to develop the model better because if you do regression here, it's very complicated. It's a system of equation,
yes,
and your parameter, the gamma, and the expression of the activity coefficient is very complicated. It's a very non-linear system. Of course, if you have I think you have the capability to do that. We
Yeah.
don't have because we're not mathematicians.
Yeah.
And then we can work together.
yeah yeah actually in this chemistry in mathematics I believe that there's an application of mathematics in the chemical reaction
Yes.
using the ordinary differential equation, and then we can build the model and fit the data using some optimization tools.
Yes.
Yeah, and find the best
I had
parameters.
long time ago a very good student
Yeah.
who's from Algeria, and a very good mathematical foundation there. And you see, a few years ago we have a paper we do we use the Dashmak matter model, and he developed the program. I think because he has the what you call the capacity to do that do his PhD. And of course we need that because I'm not a mathematician.
Yeah.
So,
Yeah. So, yeah.
that's why where we need
Yeah.
help. So if you find that you can contribute whatever you can, because you can share our experimental data. We have other experimental data, not only with MIT.
Yeah.
With MIT, we are a little bit constant because of the agreement. We have 3 years agreement, and American. Some American here maybe
Yeah.
are online, but of course they're very strict in terms of agreement and this. But
Yeah.
we have a lot of other data because we work on developing other solvents where maybe the constant are not known, where we need the data regression to get the constant that fit the experimenter. So we can collaborate on that.
Yes. Thank you. Thank you very much for the explanation. It's very challenging.
Even we can have
Yeah.
a student, can be student, new student, because
Yes.
with Dr. Khalil, I have a co-supervising a master student. I'm not
Yeah.
sure if she's
Yes.
here or no?
Yes, yes.
She's here?
I think she's in here somewhere.
Okay.
Yeah.
Because with the mask, we don't know
Yeah.
That's true. That's true.
anybody
Thank
there.
you.
So it is that it's another possibility because I believe that the best way to to get the collaboration working is through
Through
student
students, yeah.
supervision.
Yeah.
Because we are busy,
Yes.
we can talk too much about collaboration,
Yes.
but the student can make it. So if you have a master student, even they can work together as supervision. Then we share the data inside, etc. So that would be very good.
Yeah.
So,
Thank you. Thank you very much.
Okay, yeah. And we have one more question.
Yes,
It's
okay.
very popular topic.
So before you go for the question, may I suggest to please stop sharing screen so we can see the speakers who are talking?
Sorry.
The screen. If you stop sharing screen, I think we can
Oh,
see
okay,
people who
yeah.
are talking.
Sure. Yeah, please.
Yeah.
Because
So I hope I don't need my slides to explain. It's okay.
yeah. Okay.
It would be nice to see people talking. Let's put it this way.
Stop sharing. Yeah. Just. Okay. Hello. Yeah.
Yeah.
Can you see us now?
Yes, wonderful.
Okay.
Thank you.
Very good. Okay. Then the next, but unfortunately, will be the last question offline. Is from Dr. Asep Saifullah, the head of department. You want to ask question to Dr. Khairuddin? Yeah. Please, Pak Asep. Oh, you can use
Thank you for the time, and we are really appreciate for your very interesting presentation in the topic of carbon capture. At the beginning of your presentation, I showed there was a slide presented the illustration that the compound can absorb the CO2, and also there is a possibility to dissolve the CO2, right? But I haven't seen in your presentation for the process of CO2 dissorption from absorption, right? Maybe I imagine that when the CO2 being dissolved, there is something quite interesting to see the speciation of the carbonated amine compound, whether or not that CO2 release, dissolve, or still being absorbed by the methylated amine compound in the solution. But it's really very interesting for us from the chemistry colleagues and also students perhaps present in this conference, when we see the mass balance, the neutrality balance, all of the constant of equilibrium presented to show the speciation and related in the calculation. Thank you very much.
Yeah, thank you. Why we are present more on the absorption is basically we want to have a very economical technology for CO2 capture and utilization. So we want to what we call eliminate the regeneration section, because the regeneration is where the cost is there, because we have to heat the solution to release back the CO2, and by heating also we increase the corrosivity, the degradation of the amine, and all the costs or the issues or the problems in implementing CO2 capture, like from the atmosphere or from flue gas, is coming from the regeneration. So by converting the CO2 as a captured species directly, like the carbamate, we regenerate the amine also, and that can happen at low temperature. And of course, electricity, as you may say, is not economical, but there is development on renewable energy. I mean, the source can be renewable energy and make it attractive. So that's the long term that we are looking at, is to integrate capture and utilization and get rid of the regeneration part, because the regeneration at high temperature. But we can do speciation at high temperature, and we are what I presented is 25 degrees, but we are working also at 40 degree, 60 degree, 80 degree. Normally, the regeneration starts to be measured compared to the absorption over 60 degree. That's why the condition for the absorption normally is around 40 degree, 30 degree to 40 degree, and the regeneration normally is more than 100, 110, depends on the pressure also. And we start to have regeneration, I mean the reverse reaction more significant when we are over 60 degree. And so we can do, and that of course at this temperature, so the evaporation of water can be important, so we have to include another equations and things. And this is how to, yeah. So, but it is possible to do the speciation at higher temperatures to, as you mentioned, to see how much CO2 is remaining, etc. So it is possible.
Okay, thank you. Because there is also the issue of carbon neutral
Yes.
issue, right? When we do the desorption process using the energy also. Okay, thank you, Bu Yuni.
Okay, thank you, Pak. Okay, I think unfortunately we have to stop here, but if everybody want to see more of Dr. K, then maybe you can come to our Department of Chemistry
Yes,
on
yes.
Friday.
I will, not
Yeah.
exactly the same thing, but
Yeah,
some
still
of
about
this will be
CO2.
there also.
Yes. Yeah.
Okay.
Okay.
you.
Yeah,
Okay,
thank you very much.
Thank
Please
you.
give round of applause again to Dr. Khairuddin, and I give the time to Tessa again. Yeah, thank you.
Thank you so much, Prof. Arawa, for such a very interesting topics. So before we end the sessions, as our appreciation for Prof. Arawa's time and also valuable contribution, I would like to invite Dr. Dede Johanna to kindly deliver the token of appreciation to Prof. Arawa. So please, Prof. and also Pak Dede to come forward. Thank you so much, Prof. Arawa, and also Pak Dede, and also Dr. Yuni. Okay, honorable guests, ladies and gentlemen, let's come to our second keynote speaker, which will be delivering his presentation through an online Zoom. Our second keynote speaker is Prof. Chandar Ahmad from Jawaharlal Nehru University, India. So he will presenting about the data-driven biology for understanding genome, phenome, and also transcriptome. Without any further ado, I would like to invite our moderator, Professor Al-Hadi Bustamam from Department of Mathematics, Faculty of Mathematics and Natural Sciences in Universitas Indonesia to lead the discussion. Prof. Al-Hadi, you are kindly requested.
Assalamualaikum warahmatullahi wabarakatuh. Alhamdulillah, wassalatu wassalamu ala rasulillah. Good morning for all of the participants, especially my respected dean and honorable keynote speaker, invited speaker, and all of the participants. This time for us now to come to the second plenary session. We have a very prominent professor in the field of bioinformatics, and we will talk maybe about data, about mathematics, and about biology, and also about deep learning and artificial intelligence. So our professor is Professor Chandar Ahmad. He is a professor in bioinformatics and also the former dean of the School of Computational and Integrative Science, Jawaharlal Nehru University in New Delhi, India. His earlier career is in National Institute of Biomedical Innovation, Health and Nutrition in Japan, and also he is a visiting scientist and has an honorable as associate professor position in Frontier Bioscience, Osaka University as well. He is interested in developing data-driven algorithm and application for biological data with an integrative perspective. His lab, called SciY Lab, aims to leverage on his past and ongoing works in the field of sequence and structural analysis of protein DNA and other biomolecular interaction, particularly their modeling through conventional and deep machine learning algorithm AI approach, and he has experience in studying pattern of global and conditional specific gene expression, single cell transcriptome analysis, mRNA, and new generation sequence data analysis for intestinal bowel syndrome, influenza vaccination response, uniparental disomy, and other critical problem in the field of biomedical research. His group has also developed deep learning algorithm to interpret ECG, AEG, and also medical image data using deep learning model such as LSTM, CNN, and also deep neural network. He is a very distinguished scholar. He has H-index 26 in Scopus and 31 in Google Scholar. And furthermore, he also interested in poetry as well. So he's right in English, Urdu, and Hindi as well. So without any delay, let's ask welcoming Professor Sandar with his speech about data-driven biological for understanding genome, phenome, and transcriptome. Please welcome Professor Sandar.
Thank you very much. Thank you for a wonderful introduction, and it's great to see you people around. I mean, see or at least feel you people around once again. I'll share my screen. So just to confirm that you can see my screen and you can see my slides changing. And this is my full screen. Can you see my full screen? Can you confirm that you can see my full screen? No?
Full screen? Is still
No. Okay.
Not in full screen.
I'll share it. Yeah. It should work now. Yeah, I think I can see also in one of the panels. Okay, so thank you, and I hope you can now see. So as Professor Hadi said, thank you, Professor Hadi, for introducing me here and bringing me back here in this meeting. And I'm sorry I could not be there in person, but we can take advantage of the technology. So since this a lot of audience here are from physics, mathematics, and other backgrounds, I start with a little poem which puts across where the data science stands in the field of in reference to physics and others. So with apologies, so this is just an academic kind of satire. Physics is fundamentalist. So I say is because it talks about fundamental laws or the first laws of nature. So it is fundamentalist and fussy. Mathematics is dumb because I'm again I apologize repeatedly, is because it is needs equations and explicit description of the systems, and yet not easy. Well, even though I was trained in physics, my PhD was in physics long time ago. That was in the previous century. And I still find mathematics difficult. But astrology, on the other hand, is the other extreme. It is hasty and crazy. Human brain uses none. For deep inside its terrain, it knows to represent, test, and train without bothering to explain. And data science rules this world, for even if a solution is transient, predictions are noisy and incoherent. They work the best for most because they are intelligent. So this is to place the intelligence, artificial intelligence or machine learning or data science, the three very related disciplines, in perspective with a kind of little bit of humor. If I go back to the older times, how science was done in the past, if we look at what Charles Darwin and Gregory Mendel did, so I don't know how many of you are biologists here, but just to give that background, the Darwin collected fossil data, and every one of us knows about Darwin's work on evolutionary theory. And all that he did throughout his life was to collect the fossil data and then put that data into science and derive a scientific hypothesis from science. Mendel too collected the data, although he did experiments as well, but essentially he collected the data, and from the data he tried to derive the laws of inheritance in plants, which form some kind of foundations of modern biological knowledge. So can we say that was Darwin a data scientist because he collected fossil data? He modeled this data to theorize evolution. He explained origin of species. So three aspects of data science: collection of data, modeling of data, and then explaining these models, which is at the core of what is called explainable AI today. But he never went to lab or performed an experiment. So can we say that he was a data scientist? Bioinformatician today thinks himself to be a big data scientist and like a bagpiper of science. He thinks that all the experimental biologists are only doing the collection or generation of data, and his job is to convert that data into scientific theory and real science. So this is the perception of a bioinformatician in his own mind. Whereas the experimental biologists, people who actually go to the lab and perform these experiments and generate this data or collect this data, they don't think so highly of the computational biologist, at least not until recently. So this is a paper that came in 2016 in a journal called in the New Experimental Journal of Medicine. And it says that the data scientists are actually the research parasites. And this is some quotation from that journal. It says that one of the concern it raises is that a second concern, or of course they have mentioned another concern, but one concern they have mentioned is that a new class of research person will emerge. And this class of people is the people who had nothing to do with the design and execution of the study, but use another group's data for their own ends, possibly stealing from the research productivity planned by the data gatherers, or even use the data to try to disprove what the original investigators had posited. This is editorial from New England Journal of Medicine, one of the best journals, one of the journals with the highest impact factors across any field of this study. And you can see that the kind of insecurity that the experimental biologist feels about the data science, is, if you ask this question scientifically, this is very valid work to do for any scientist to go ahead in the productivity which is planned by the original gatherers, to be able to disprove what the original data gatherer wanted to prove, and to be able to look at the data in an original way. This is a legitimate effort of a research scientist, but an experimental scientist of the highest stature can become sometimes insecure about it. And there are there is a concern among some frontline researchers that the system will be taken over by what some researchers have characterized as research parasites. So this is the term that was used not long ago, 6 years ago. Then, the researchers are aware of the developments in the field, and then a reply to this article came in the next year, 2017, and it says all biology is computational biology. All biology is computational biology. Or when I presented in the beginning of this talk, the evolutionary theory, the theory of genetics, the foundation of genetics from Mendel's laws, are essentially computational biology. This article says that without computing, you cannot integrate the outcomes of experiments. You do your experiments in isolation. One group does one experiment, one group looks at one side of this story, another group looks at another side of the story. There is no experiment that you can perform to automatically integrate the different sides of the story that come to you. It is only the computing that can do. It is only the data-driven science, because and computing would probably do through the through mathematical modeling or through other models, but these models may be too difficult to form, and therefore some kind of automated methods of integrating the scientific knowledge emerging from multiple experiments from multiple directions has to be developed, and that can only be done with the help of computational biology. And I would extend this argument, because the audience here is not all biologists. This argument probably can be extended to all fields of knowledge, including the experimental physics and other experimental chemistry and anything perhaps. The integration of knowledge that is generated from data gatherers, from the data producers or collectors, can only be performed in a computational context, in the modeling context. So it does not mean that the original data generation is an easy task, or it doesn't have to be thanked, but computational biology or computational sciences have an inseparable space in studying science altogether. Without computing, science cannot progress. Science has not progressed without computing in the past, and science will not progress without computing in the future. So here are some more examples from other fields, and fields which will connect to more of you. When we look at the research that was done by Newton, Newton's laws of motion, Newton's laws of gravitation, they were essentially an extension or some kind of a data science, because the data was actually collected by people who were studying the planetary motion, the astronomical objects and the positions accurately. So this painstakingly they were correcting the data, but this data itself was not sufficient to tell how the universe moves, why certain astronomical objects have a longer time period, why they have a longer day, why they have a longer year. So all this was not, one could not explain unless they could be put together in the form of certain laws. And these laws were then produced from the accurate interpretation and accurate fitting of models onto the data that was generated by the scientific observers. If you look at the birth of quantum mechanics, the data again comes from this collection of the solar spectra, the hydrogen atom spectra, and the series that were collected by different researchers. They could not be explained without having a good, robust mathematical or scientific model, which can actually convert that data into equations, which could convert data into models in a general sense. So the Bohr's model actually showed that these hydrogen atom spectra can fit very well on a mathematical equation, 1 upon n1 square minus 1 upon n2 square. And by formulating this particular expression, the whole foundation of quantum mechanics could be laid. Then the protein structures, there was a lot of data collection that happened when few protein structures were available, and the first principles of physics could not be applied to understand how the protein would fold there, because there are so many atoms, and if we were to write down the forces that experienced by each atom, Columbian or any interactions that are experienced, and as a result what kind of a structure will be formed from the first principles. Even today it is very challenging, although AlphaFold and others have made great success with the help of data science again. But in the very early stages of when people were studying protein structures, they were just simply collecting the data that if there is an amino acid X, then the dihedral angles alpha, the phi and psi, they are related to each other. So they identified there are certain areas in this plot of phi psi, which is called Ramachandran plot, certain areas which are viable or which are possible, where there are other areas which are forbidden, that the atoms in a protein cannot take those areas. That means phi psi values cannot combine in those particular combinations or configurations. So this was an effort purely driven from data. So why I'm highlighting this is that the different studies in the past have great science has come in the past from the analysis of data, and then data was converted into empirical science first, and the empirical science was related to the first principle trying to produce the outcomes of the experiments, and experiments trying to explain to fit themselves into the existing, or if when the two could not be married together, then the new laws were generated. So then, but in the past, we never said that we are doing data-driven science or we are doing data-driven biology or anything. It was kind of natural component of any scientific research. So what happened today? Why the data science has become a buzzword? So let us just see in the contrast as data science was done in the past and as data science is done today and how we have changed. So in the past, the data analysis was limited to visualizing data, putting some curves and then some data points, and then putting some mathematical equations onto these data points, doing some basic statistics, and trying to always relate it to what is already known as fundamental laws. And if not, then trying to create new laws or empirical laws. Then came the field of knowledge in data science or artificial intelligence, which said, oh, we don't need the mathematical equations. We don't need Q1, Q2 upon R square. We do not need G, M1, M2 upon R square. We can simply put everything, every data into a multi-layer perceptron, data in, data out, and some black box like of a model can be produced. This black box, I don't know how this black box look like, but this black box has the power that if you give new data to this side, new outcomes can be given. So instead of writing a Coulomb's law or instead of writing the Newton's law of gravitation, we now had a black box in the field of data science, which led to the foundation of the machine learning or artificial intelligence, where intelligence, when we are, so why it is intelligent is because we as humans, when we do an intelligent act, we do not really bother to explain explicitly why we have taken a decision that we have taken. Our decisions are considered intelligent based on the results they produce. So artificial intelligence, at least in the early stages, was not too bothered about explicitly formulating or explicitly telling why it is giving an answer that it is giving. The main idea was that we have a data and the data says, this is my input. And if I give this input, this should be the output, producing a training data. And based on that training data, I generate a model, what this shape looks like, what the model is actually, what is the mathematical representation inside the model was nobody's concern. The only concern was that after having trained my model on this data, if I get the new outcomes, new data, in which I do not know the outcomes, I do not know the one side of the data, that this is my input, this is my output. If I have new data in which I do not have the outputs, I only have the inputs. Can I predict these outcomes? So the predictive aspect of the model became important. The ability of the model to predict and kind of, as we call in the computational science, is the ability to generalize. So not ability to fit, but ability to generalize. This is another thing. So if we have data, we can do a curve fitting, but this curve may not fit very well on the new data. So models were concerned about whether it will generalize or not, whether it will generalize, what kind of model will generalize, which features are important, which features are not important. That is the only concern that people had at the time. People did not were bothered about the detailed structure of the models. That is the fundamental difference between the way the empirical sciences was pursued in the past and the data science that is pursued now. Of course, we have gone one paradigm ahead of that now, and we are now going from the traditional AI to a field which is called explainable AI, where we also try to interpret our models, but the interpretation is only to the extent that in my model, these particular features are important, these features are interacting with each other. Still, we do not have to write the detailed mathematical formulation for most of the artificial intelligence based or machine learning based models. So now I give you some examples of how we have utilized this power of machine learning over the years in our lab and in our research. So I take some examples from biology. I'll try to simplify them so a physicist and mathematician can understand what is going on in this. So transcriptome is basically the information about in the entire genome certain genes actually express. That is, they make proteins. Certain genes, most of the genes are not expressing in a given cellular condition. So what genes express at a given time tell the cellular state and the condition of the living system at the cellular level. So now in the field of biology, a lot of people have performed these experiments on collecting this transcriptomic data. And data from almost, if you look only at the human, that about 20,000 or more genes data has been collected in hundreds of thousands of conditions. So now each of these conditions, so we can say that we have the gene expression profiles. We have, let us say, 200 or 300,000 gene expression profiles. that is under different cellular conditions. When we give this drug, what happens? When a person ages this, what happens? When in this cell, what genes are expressing in this cell, what is happening? So we have under a large number of biological conditions, we have researchers have collected the expression data from various technologies. The technologies could be microarray technology, next generation sequencing technology. So very different technologies have been used, but the primary goal of studying transcriptomics has been that if this is a particular cell, this is my eyes during developing, this is my teeth developing, this is my lungs developing, and if this is my disease, if a person has cancer, his cancer cell, his non-cancerous cells, his metastatic cells, all different types of biological conditions, what is the state of the gene expression, different expression of different genes in these cellular conditions. And under these large number of conditions, people have collected expression data. So now these experimental research, experimental investigations are working in silos. One side of the data does not know about another side of the data. Somebody is studying one type of cancer, another is studying another type of cancer. Even sometimes two groups of researchers studying the same type of cancer, but in different individuals or under different at different time points. So all this data has been abundantly produced, and this is a gold mine for doing research. So who will combine, who will put this data together, and who will be able to tell something interesting and integrate this biological question about under what condition, what happens. So we can ask instead of going to the lab every time and performing these experiments and collecting samples from humans or other species and collecting the gene expression data every time, we can perhaps ask many novel questions from the data itself. What happened if this gene changes? What happens if this gene is expressing? What other genes are expressing with it? All these questions can be asked without ever having to do a biological experiment. So this creates a tremendous opportunity for asking questions directly to the data and getting answers directly from the data and getting there in return the scientific theories, scientific foundation of an integrative biology. So biology, which is studied in a scattered manner, could be combined into new laws, new understandings, and new patterns that are otherwise invisible. So in this example, what we did was that there is a TLR pathway, which usually acts in the case of the pathogen attacks an individual, then there are toll-like receptors, which initiate the immune response. Now, this TLR pathway acts in two different ways. In one case, it takes help from another gene, which is MID88. In another case, it does not take help of MID88. Now, certain organs in the body are affected in one particular way, and others are infected in another way. Certain individual differences are there, disease-specific differences are there, pathogen-specific differences are there. So how can we model that, and can we collect this data? So what we did was that we collected all this data, that is different 2,326 technologies have been used to collect this different types of expression data, and we just asked a universal. So at the time of this study, when I performed this in the beginning, we had 95,000 samples on one single technology called Affymetrix U133 platform. And then when we started looking at it, we just analyzed what is happening to different genes. And the problem with this, so the challenge of analyzing this data is that data is not written in the repositories in a very effective manner. So for example, I give you these examples. One study deposited a data and it said about source name, healthy individual. Another group deposited a similar data, and after source name, it writes peripheral blood mononuclear cells. So if you have to write a computer program that has to take advantage of these different natural language annotations in the data, they are not easy because the program cannot really make out anything from it. So the processing of the natural language in these data, the header or the metadata as we call them, and relating them to the biological condition is a big challenge. So what we did was that we collected the set of genes from MID88 dependent TLR pathways, MID88 independent pathways, and then we collected all the samples where this pathway, one was active, in another case where the other pathway was active. So we got this is the protocol of the experiments, but in summary, what we did was we found some thousands of experiments in which MID88 gene was expressing, another few thousand of experiments in which this gene was not expressing, and then we started looking at the metadata on the top. That is, what is the biological condition we can derive from it, even though biologists may not know explicitly what is the difference between the two pathways and which organs are affected more in one pathway. So what we did was we first started looking at other genes which are expressed with, in the case of mediated being present or expressed, and being not present in the expressed. So we identified certain new genes in this, and predominantly we found that there is a kind of clustering of certain genes which are expressed together with mediated, and some which are exclusive in nature. So that is, we found these two clusters, and the co-expression within this pathway of mediated dependent genes, and in the absence of these, could be detected just simply analyzing the data, that is, that the profiles which were present in the, and then when we combine the natural language and certain, just the word enrichment could tell us about how the two types of data differ from one another. We could not, because the data was not explicitly annotated from which part of the tissue it is coming, from which type of individuals it is coming, what is the property of this data, all this. So we just took all the natural language annotations and analyzed their natural language, and then found that some words were explicitly in the mediated dependent pathway, some were mediated independent pathway. So we could distinguish that certain organs probably express one type of pathway more frequently than the other. So with this example, so I would come back again to the philosophy of how data science is growing and how the data science has been done in the field of biology, including my own story and how we have approached this over the last 2 decades of our research. That in the first paradigm, what we were doing was simply doing some basic statistics, trying to fit our curves, so even basic statistics of the data could reveal something very interesting. So then we started applying the machine learning, the supervised machine learning training, and the clustering, which was unsupervised. And we started going to deep learning, natural language processing, artificial intelligence, cloud computing, the resources, the way we look at the research. So I'll give you some more examples about the 3 different paradigms in which we contributed, how differently we pursued some of the problems and projects of biological questions. So one question was, for example, to annotate proteins, and that this is the work that I started in 2004, and in 2004 some very interesting results we were able to produce. And that was the time when people used to look at machine learning, which particularly biologists used to look at machine learning with a lot of suspicion, and they did not really trust machine learning. And the main question was that what is this black box? You are saying that you are able to predict secondary structure of protein, but what is predicting secondary structure? So because scientist was very invested in trying to understand the basics and the outcomes of the answers, and actually very rightly so, because science is not science unless science is not just looking for the right answer, but science should also try to find why this answer is coming. So that is, they were invested in that understanding. But at that time, we started looking at these proteins, but we cannot wait for the principles. Sometimes we need an answer. We do not need complete understanding of why this answer is working. So as long as this is working, so we have to have mechanisms to understand that a particular question answer strategy is working. Why it is working, what is the mechanistic basis of its work, may be understood later. That is what is the approach of data science, that we first try to get it work, and then later on we can try to understand why it is working and what is the mechanistic basis of it is working. So at that, in that background, we were trying to look at the proteins, and we were interested in DNA binding proteins, the proteins which interact with DNA. When they interact with DNA, they kind of do multiple functions. For instance, they actually go to the genome, they interact with the genomic DNA, and they tell a particular gene to express, a particular protein is formed. That is the whole foundation of life sciences. Or they may be there, these proteins may be there, and as soon as a pathogen attacks an organism in the cell, they notice that there is some new DNA. This DNA does not belong to the person in which I am sitting. So they can recognize the attack of a pathogen with the help of the DNA of the pathogen. So their proteins have this ability to distinguish the DNA of the individual, or what we call host, and the DNA of the pathogen, the attacking organism. So if they lose this ability, they cannot perform, the immune system cannot work. in this particular aspect. So this question of identifying DNA binding proteins from a large number of genes was and is still a big task. How can we say that this particular protein binds DNA? Whatever, then later on we'll further detail it, whether it is a transcription factor or whether it is a pathogen recognizing molecules or it is just packaging the DNA. But first level of annotation would be to label them as binding to DNA or not. Can you just update me about time left? So I go with the... We are halfway. Sahadi?
Yeah, you still have 20 minutes for presentation. Yeah.
Okay, thank you. So in that case, so when the protein structures were known and we wanted to know whether this protein will bind to DNA or not. So one strategy that people were employing at that time was the scientific physics-based strategy that since DNA has a negative charge, so proteins which have a positive charge should interact with DNA. And therefore, they were trying to identify the charge patches on the proteins and all. And it was working, but it is a complex process to look at the structure, to try to solve the charge patch problem, etc. So what we took was a very simple approach that just look at the total charge of the protein. And total charge of the protein does not have to be an accurate charge. We can simply count the amino acids. Certain amino acids are known to have a positive charge and certain amino acids are known to have a negative charge. So we simply add the number of positively charged residues and subtract the number of negatively charged residues and the total charge. If the total charge is positive, there is a likelihood that this protein is a DNA binding protein. Simply from data, we try to estimate that if we make this hypothesis, how many proteins can we correctly identify as DNA binding? So what we found was that yes, it works in a large number of cases, but there are still number of proteins which have a net negative charge, but they do not bind to DNA. So the next question is, how can we identify some property of these proteins which have a negative charge, but they still bind DNA? So what we did was that we started looking at the dipole moment. Now, dipole moment has to be measured in the experimental lab, but we can simply, I defined a very simple rule of calculating dipole moment. If I know that this amino acid is a positively charged residue in the case of proteins, I can simply find some location, approximate location, or where I can assume this protein, this amino acid to be present, and I can assign a charge there +1. So I can roughly estimate that this is how the charges are polarized in this protein. And then based on that polarization pattern, I can estimate a rough estimate of the dipole moment of this protein. And same way I can calculate the quadrupole moment. So when we looked at these three properties, the charge, dipole, and quadrupole moments, it was wonderful. Just three properties modeled using a quadratic equation. We were able to linear programming actually. We were able to predict 90% of the proteins correctly. The DNA binding proteins, either they should have a net charge positive or they should have a high dipole moment or have a quadrupole moment. And if we combine three into a single predictor, we can make a very good job. We can do a very good job of predicting. So then subsequently, we started looking at other aspects of data because many times when protein, now a physics-based approach that is applied to study protein-DNA interactions is people dock protein over and DNA together. But many a times what happens is the protein is changing its structure during the after the interaction. So how can we model that? So we looked at the conformational changes, as we call them, the conformational changes that the proteins undergo, and we characterized and grouped them in different categories. And these different movements could be collected simply from the data. So the point that is important here is that this good science, the laws of mathematical formulation that we were using, or the data science technologies were we using in these problems, but not very complex. They were very simple. We were just looking at statistics. Total charge here and total charge here. What is the difference between them? Some very simple statistics. How can we get great science from such simple statistics? Everybody knows this is statistics. Why the great science? Everybody is not generating that great science. In this scenario, the most important thing is the quality of data. So quality of data becomes critical and crucial for solving problems with simple laws. And the discovery of simple laws is impossible if the quality of data that you collect for your study is not good. So therefore, the data science, basically the first step of data science also starts with a very high quality of data. And therefore, the role of the people who originally collected this data and then the pre-processing of the data, whether I have to normalize the dipole moment by the length of the protein or not, whether I should take the absolute charge, should I normalize with the total length, or should I normalize with the square root of length? So these kind of questions, whether the charges are actually increasing linearly, so how to pre-process the data so that the multiple experiments that are generating the data together can be combined and an integrated story can be created out of them. So pre-processing and these technologies become important, and there you cannot simply put the data together and apply. So now different approaches to pre-process and bring the different data generated independently onto the same scale have been approached. For instance, in the case of microarray, the batch effect, even the same group who do experiments in 1 year and experiment in another year, their data do not agree. They do not agree because the quantifications are different. Multiple factors contribute. So what they call is batch effect. So how normalization strategies of data science become important even before you apply machine learning or even before you apply simple statistics. So the quality of data and quality of pre-processing the data, quality of annotations of the data, quality of removing the redundancy and repetitions from the data become fundamental to achieving success on such kind of stories. Then we went to the next step of like we were looking at if I know that this is a DNA binding protein, can I tell which amino acid residue in this protein is actually interacting with DNA? The problem of predicting DNA binding sites from sequence. So we developed the first machine learning methods in this again in 2004-5, and we continued to work on different aspects of this problem until recently, and we still work on different aspects of this problem. There are many new issues that we have identified in this. So here we said, okay, if I can develop a statistical model or a machine learning model to say that arginine is a positively charged residue, therefore it should more frequently interact with DNA. Lysine is a positively charged residue, therefore it should interact more frequently with DNA. Okay, if I now have a sequence, can I really tell which part of this protein is actually in the interface with DNA? Because this has implication for intervening with the life's process. If I want to make a drug, I want to stop a particular protein DNA interaction, or I want to enhance the interaction. I want to change that particular position. And I can also explain this individual has a mutation in this location, and therefore this individual will behave differently or respond differently to a drug. So this has huge practical implications. So can I exactly identify which amino acid residue in the protein is actually interacting with DNA? So I can simply do the basic statistics that I was saying. I can try to identify how many times arginine is in their phase, how many it is not. For 20 amino acid residues, I can calculate their propensities. But one amino acid is not enough for the interaction. Therefore, I have to go for 2 amino acids, so dinucleotide, dipeptide. But as soon as I go from one amino acid to dipeptide, I have now 20 into 2, 400 dimensions. And if I want to take 3 amino acid window, my dimensions become 8,000. So my number of dimensions from 20 to 400, 400 to 8,000. So as slightly increasing the window, my number of parameters that I want to now train, or the number of parameters, statistical parameters that will emerge from a simple basic statistical analysis will be huge. I do not have so much of data to get these parameters confidently from the knowledge of interactions. So what do we do? So machine learning helps here, and neural network says, no, you don't have to find explicit relationships. You don't have to do naive Bayesian classifier. What you can do is you just put these 20 amino acids in some representation, each amino acid with 20 dimensions or 20 inputs, and just make a hidden layer, which will combine this data in a complex manner. But you don't have to explicitly model what kind of complexity is there, what kind of products are being used, what kind of additions are being used. Some implicit model will be created, and this implicit model will be very accurate. And that is what we did in 2004. And this worked excellently. We avoided kind of training our model too much and making our model too accurate on the data in which we create that model and failing on the new data. So this generalization approach, we developed this, some very highly cited and very well-received papers were the product of this analysis. And we could model using the multi-layer perceptron neural network, these models, which work effectively. And then we started looking at the conservation evolutionary properties of these, and these again generated some very nicely received works. reports and results where we also identified the clusters of conserved residues which can be utilized in a structure to predict the DNA binding sites, and therefore in different types of proteins, whether they are packaging the DNA, whether they are binding to zinc coordinating proteins, the metal based, and or they are helix turn helix, so different kinds of major group, minor group, different properties of DNA. And then these new concepts we generated from pure statistical analysis and with the introduction of early stage machine learning models. But then I will gradually converge on this, how we utilize this for the transcription factor binding sites. This is another very interesting story. If you look at the, this is an experiment I would like to share with you, that there is a transcription factor called STAT3. And people are interested in about how STAT3 works, because this has an important role to play in immunology. So people have done experiments to see what kind of genes are regulated by this transcription factor, because gene regulation by transcription factors is fundamental to the understanding of transcriptomics. So people, 4 different groups did this experiment, and they collected the genes or the sequences that this transcription factor targets. So in different 4 cell types, the macrophages, CD4 plus T cells, ATT20 cancer cells, and embryonic stem cells, then this data was reported individually. We collected this data, and from this data we analyzed whether these are, in these experiments, are there some targets which are common. Only 35 sites were common, whereas thousands of sites were reported only in one experiment. So what is happening? Why this transcription factor has a completely different regulatory program in one cell and totally a different program in another cell? So this question is, now the protein is the same, the genome is the same, and the targets are different. Why this is happening? So this is the question that we try to answer from by looking at the structure. So this is the another outcome from the same analysis, but what we propose this model, that it is not just the target position where the protein binds which is important, it is the surrounding region which is also very important. Because in the genome, when a transcription factor comes and it has to bind at a given location, the genome is very big. The transcription factor has to find where its target is. And so the surrounding regions, the flanking regions, and the distant regions, which actually do not bind to this transcription factor, have a role to play to send this transcription factor to the target quickly. So we defined, by looking at this data of different reads, we found that different 4 cells have slightly different type of genome folding, or the chromatin possibly. This is what we hypothesized. And that in some cases, the key position where the transcription factor binds is the critical position. In some cases, the surrounding regions have position, and the way the information is distributed around the motif is different in each cell type. And it is the difference between these folding patterns around the central motif that could be utilized to not only identify the differences between the cell types, but also to identify the commonality that was missing. Why this site, what is common in this type of sites and this type of sites, apparently at the levels of sequence, they don't look very similar. But when we convert them into the shape signatures, and we develop our own methods to convert sequences into shape signatures, so when we utilize those methods, we were able to explain the transcription factor binding patterns of STAT3, and when we extended it to other transcription factors, we studied thousands of transcription factors, and we found that each one of them has a different pattern of where the information is distributed about its binding. So we identified 4 clusters of transcription factors, 229 transcription factor in this, and 504 in the last one. So just to give you the numbers. So, and the information that is present about the binding of transcription factor is distributed in different shapes in these. So another project that I would quickly introduce that we have been doing in our lab is an integration of gene expression and the sequence analysis. Here the issue is that people tell about the function of a protein by looking at the sequence and possibly its structure. But the the sequence and the structure of a protein is common in every cell and every individual. Then why that this function is performed in some places, but it is not performed in other places? So this is a question. So here we distinguish between the potentiality of a function and eventuality of the function. Potentiality of the function means that this protein can perform this function. But eventuality of the function means whether this will actually do that function or not. Whether it will actually do the function depends upon what other proteins are present in the cell, whether this protein itself is expressed or not expressed. So can we link the two together? The one information about the eventuality is coming from the gene expression, and the potentiality information is coming from sequence and its structure. So we developed our first method to integrate the two methods for the purpose of annotations, and especially for the DNA binding proteins. And we found that the expression patterns of the two can be combined to improve the accuracies. So the details I can't give because of the time, but broadly some information is shown here, and the paper can be read for more details. So other than this, we were also looking at annotating protein from sequences using evolutionary profiles, looking at the ECG data as was mentioned in my profile in the beginning. So I think I will not go into the details of them. I'll primarily stop here and would rather discuss your questions, and so that I can remain connected to your interests. But to just give a summary, that data science has always been fundamental to the scientific analysis and discovery. Field has moved from simple statistical analysis to classical machine learning, and now deep learning and explainable AI. And whether we use a shallow model for modeling our data or a deep model of our data, it depends on the complexity of our system. And we should not be swayed to find the most complex model for our data, because they may not be appropriate for the data that we are dealing with. So with this, I conclude with this, again, another poetic note: mimicking brain, shallow and deep. Machines learn when man is asleep, without complex equations or laws, making use of errors and flaws. That is how the machine learning model works, because you need error and you minimize error. So making use of errors and flaws, regressive, divisive, and classifying. These are all terms in machine learning. Regressive, divisive, and classifying only in AI are so gratifying. That's all from my side for today. I'll take your questions.
Okay. Thank you very much, Prof. Sandar, for very what is it? Breaking the ice. Yeah. I think this is very interesting because in our university now we also working using a multidisciplinary approach using data science as well, and we work together with many departments and also many faculty. I think the key point here is how we move forward from traditional approach and using a new era of data-driven knowledge. Yeah, how to build knowledge based on data. And then that is we are very happy because you are presenting here in the field of bioinformatics, because in our faculty this field also represent in many different departments. For example, in mathematics we are working mostly with algorithm, and also department of chemistry using like structural analysis for protein interaction also, and with biological department. So I think it is quite interesting if we get the audience now to have some question and answer. Is there any question and answer from the audience? Maybe from biological department. Yeah. Pak Anom ada nggak? Tadi ada Pak Anom. From biological department, from chemistry, I think Pak Budiawan, ya. Yeah. Yeah.
Thank you very much.
Pak Budiawan is our vice dean, academic dean.
Thank you
He's
very much.
from chemistry department.
Thank you very much, Professor Sandar, for your nice presentations. Yeah, I just would like to know your comment. Yeah, what is your suggestion? Is this enough if we are studying about protein interaction with DNA, as you mentioned before? So is it just enough for just only modeling, or we should also lower to I mean the laboratory in practice. I mean to experiment about that. What would you suggest about that? Thank you very much.
Okay. So as I said in the beginning, the caution that of course we do a lot of experiments, a lot of data is generated, and not all the science that can come out of these data immediately comes out. And a lot of this science will come out after combining the outcomes of various experiments performed independently. And that is one role for biology, for the computational biologist, which is independent of working in collaboration with biologists or not. Another role for them is to also design the biological experiments properly so that the outcomes that are made, for instance, most of the biology also has become a high throughput biology now. You do not collect data of one interaction, you collect simultaneously data of so many interactions. You don't do just one-to-one. Of course, high resolution experiments are also performed, but most of the experiments today done in biology are generating lots of data. So that is where, again, this is a supporting role for the bioinformatician to try to make sense out of the data that the biologist is generating. Here, these computational scientists should be ready to take a secondary position and try to help the biologist to find the answer to his questions. The role of generating the original data does not end. It will remain always the first thing. Ultimately, the computational biologist also should generate a hypothesis that can be tested. Just giving a new theory without anybody having to test it will not work. So generating original data, collecting the original data will always remain important, and it will not go away. But at the same time, the realization of full potential of the data that is generated, that is where the computational biology has to play a role. And sometimes an experiment need not be performed. The answer to that the question that the experiment is asking may be already present in the data in a different form. That is where the redundancy element, the element of the computational aspect has to take place. And but again, with that note and with all celebration of the computational biology is not going to replace the experimental biology or experimental science of any kind. That will remain the ultimate science. And because unless you can test it in the laboratory and unless you can produce the right kind of data science will end up into some dead end. I mean, if we are doing image analysis, but if you do not go to the lab and ask a doctor what this image is representing, so this histological labeling of the data, if you do not have well labeled data, you cannot develop a model based on the images. But then once you have a model and once you have a deep learning model which can look at your X-ray images and can tell you whether it is COVID or not COVID, now if you go back again to the doctor, it is a waste. Let the doctors do something new, something more interesting, and something where the machine is not working yet. So that is, I think the two sciences will work hand in hand. They have to work together. And one should not think that there is a substitute for the other.
Thank you, Professor. This is a very interesting point. Both of these experiment and data science should coexist, work together to have the answer. Yeah. Is there any question from audience or maybe from Zoom? Okay, Prof. Sandar, I have a question. Because you said before that the quality of data is the key for the data science. So that is the problem in many area for data science, including in biological experiment area. So how you suggestion to how we get the valid for the best quality data for data science? Do you have any tips about that?
So my quick thoughts are, first of all, the generating high quality data is the responsibility of the primary data producer. But it is not just about the quality means right and wrong of data. quality also means the kind of diversity in the data, for example. If I'm studying a population and I'm creating a sample out of it, am I creating a sample which is representative of my population? So having sufficient diversity, having sufficient representability in the data, that is also equally important. That also is part of the quality of data. So this is the first level. And the second level is when you process the data so data may be originally very good, but if you are not processing as a computational scientist, if you're not dealing with this data correctly, you can convert a good quality data into a useless data, because you do not understand the scaling of the data, the quantification of the data that is done in different experiments. And if you do not understand how particularly the quantification and the labeling that have been associated to the data, if you have not understood it very well, if you have not sit together with the people who are familiar with this data, then your good data quality can easily convert into poor quality. So as we say in the modeling, the AI field, GIGO, like garbage in, garbage out.
Yeah.
The machine learning model cannot do better than the data. But again, it is, first of all, the responsibility of the original data generator. Secondly, the one who analyzes, who puts the data, multiple data together, it is their job as well. Third is that even if you are given a data which is noisy, which has a lot of problems, now you can develop some computational strategy to identify the problem with the data. This is also an area, again, where computational scientists can contribute, that they can analyze the data, they can look for the consistency in the data, and based on the consistency, they can comment on which data is probably a valid data and which data is probably invalid data. So these are, again, multiple levels at which the quality of data is improved. And some data is completely unusable, and not because the quantification is not correct, because labeling is not correct. There are a lot of missing values. But see, if you look at the single cell transcriptomics, 70 to 80% of the genes have missing values in a given experiment. But still, people work on that data, and people have generated very powerful outcomes from those analyses. So dealing with data with a lot of missing values, again, somebody could discard this data. This is a poor quality, but then there are ways to utilize this data. So quality also refers to about what kind of information is contained and how we can best utilize them as the end model experts of modeling.
Okay. Time is up. Yeah. Okay. Maybe for my last comment. Actually, in our faculty, we are working now in different field of bioinformatics, and some in department of mathematics. We are related with the gene expression as well, how to conduct missing data as well. And then now in biological department, they are also conduct new course about bioinformatics, and also in faculty of chemistry. So maybe in the last comment, how we get ecosystem to make this like a good collaboration in the field of data science. Maybe the key point I saw in your slide about trust. Maybe you can add one comment about this. Thank you.
My quick thoughts again, since this is more about the management of the scientific professionals and kind of administrative aspect, and also the personal collaborative aspect. So first of all, transparency helps. So if many times a biologist would not give you your data because they think that you will take the data and publish a paper without having them on board, or may have produced something useful for that. So when we start collaboration, we should be very clear about how the data will use and who will get what credits. So right in the beginning, don't leave these questions to the end, that in the end we will decide who will be the first author, who will be the last author and all. You start a project with clear roles for each one. This is one way of building trust. And then ultimate goal of, although we might say that our ultimate goal is to produce great science, but that is not really true. Our motivation to do good science is also professional success and our own career growth. So we have to be respectful to each other. Then we have to develop a kind of teams which have develop common professional and scientific interests. So the professional interest should also converge in some way, that if we achieve these goals, this is what this group will be able to achieve. This is what this group will be able to achieve. And the scientific outcomes is in the sense that we want to solve the problem of, say, we want to develop a good drug for this particular disease. So the scientific outcome will integrate people who are working on different aspects of this, and the professional promise and professional transparency will do. So this is how the motivation works. So and sometimes it is good to start with a project. When you write a grant, you write, this is the bigger problem we want to solve, and then we identify clear roles. This is the role for this person, this is the role for other person. One problem that sometimes happens is that people do not share their data because they are not confident of their data. So that is another thing. So one thing is that they are not confident of the people with whom they are working. Second is they are not very sure whether their data is really correct or not, and they are afraid to making their data or their program public. So to them, my message is that every data has some problems. Do not be too harsh on yourself about the quality of your data. Try to make it a long-term goal to keep on improving your data, to keep on improving your codes, keep on improving your scientific outcomes. Make it a long-term goal, but do not stop working because of the fear of your data will be noted for errors. Let the errors come and the errors get removed rather than keep holding them back. It is like you go to the doctor, you have to tell your disease. You cannot just hide your disease and say, no, I don't, this is too personal to me. So same way, your data will be cured by the doctors, and many a times data is corrected by the community. And there's nothing wrong in your errors being found with your data, but be transparent about it. Do not deliberately make wrong data, and do not overestimate the quality of your data, but systematically keep on improving your scientific goals. And do not be too harsh on yourself or to your collaborators. Try to build do not idealize that this is what I want to achieve. Go incrementally from where you are and to where you want to be.
Okay, I think time is up. Thank you very much, Prof. Sandar. Please give a big applause for Prof. Sandar.
Thank you very much.
We conclude this session. Terima kasih. Assalamualaikum warahmatullahi wabarakatuh.
Thank you so much, Prof. Shandar Ahmad, for such a very interesting topic. So before we end this discussion, as our appreciation for Prof. Ahmad's time and also valuable contribution, may I invite Prof. Al-Hadi again to kindly deliver the e-certificate to Prof. Ahmad. The committee will be displaying the e-certificate on the screen, and the soft file will be delivered to Prof. Ahmad's email accordingly.
Okay, in the name of the ISCPMS committee, we proudly present our certificate of appreciation to Professor Sandar Ahmad. This week, applause. Thank you, Prof. Sandar Ahmad.
Thank you so much, Prof. Al-Hadi, Prof. Ahmad. Ladies and gentlemen, we will now have a break for lunch and also Zuhur prayer. Parallel session 1 will be starting promptly after the lunch break at 1 until 3 p.m. So for the participants who are here with us today, the lunch will be having in front of this room. And for those of you who are joining through the Zoom and leave the meeting during the break, please join again the Zoom meeting 10 minutes before 1 p.m. So thank you very much and have a nice lunch.